Hello everyone and welcome to my trial lecture. I would like to start by thanking my committee for giving me such an interesting topic to discuss and to read up on over the last couple of weeks. My name is Sara Blichner and my title for today is Anthropogenic Climate Change, Exploring the Drivers and Impacts with Earth System Models. Let's start by just exploring the title a little bit. So exploring the drivers and impacts with Earth system models. This can be interpreted in at least two ways. One is, what do ESMs tell us about drivers and impacts? So that would be extremes, precipitation, circulation, etc. So basically looking at what the Earth system models do when we run them. And the second question would be, what can Earth system models tell us about drivers and impacts? So this is more along the lines of what do we, how do we use them? Are Earth system models an appropriate tool? Are they better than other models? And what are the uncertainties in Earth system models? And in this talk, I'm going to focus more on the second than the first question here. What to expect in the next 45 minutes? I will start by giving an introduction where I will more or less go through the words in the title. So anthropogenic climate change, impacts, drivers, and Earth system models. Then next I will move on to discuss detection and attribution of climate change. So is climate changing and why? In part two, I will talk about using Earth system models to predict the future, and I will especially focus on CO2 and aerosols. And then in the last part, I will try to give an outlook and some possible futures for Earth system models and how we should move forward. First, let's have a look at this beautiful, in my opinion, time series, going all the way back from year 800 up until present day. And it's showing the full flowering day of the cherry blossom in Kyoto, Japan each year. And it's showing the days after the start of the year. And I want you to notice two things about this time series. And one is that it's quite noisy. There's a lot of variability. One year, the blossoming might be very late. The next year, it might be quite early. And this is because climate is quite noisy. There is a lot of internal variability. And then I want you to notice that after the pre-industrial revolution, which is roughly here, we can still see that something is happening. The trees are blossoming earlier and earlier up until 2021, which had the 26th of March, which is the earliest blossom on record. And what you see here is anthropogenic climate change. The temperatures overall on the Earth are getting higher. So what are the impacts of this change that we're seeing? Unfortunately, it doesn't limit itself to influencing when the cherries blossom. We're already seeing impacts of climate change, but due to this internal variability, it's often very tricky to attribute single events to climate change. But overall, we see that it is changing. I'm just going to mention a few impacts that we're already seeing and expect to see more in the future. So firstly, with increased temperatures, we expect increased droughts. And with that also, for example, more forest fires. Especially regions that are dependent on meltwater are expected to experience more droughts because less snow is going to accumulate in the mountains. And then secondly, an atmosphere which is warmer is basically an atmosphere which has more energy. So we expect more intense storms in the future. Additionally, a warmer atmosphere can hold more water vapor, which means that we also expect increased extreme precipitation events. And then lastly, I just wanted to mention one example of an impact to ecosystems. And what you can see here is the Arctic sea ice minima of 2020. And then you can see the median extent from 1981 to 2010. And you can see that it's shrinking. And what that means is that the ecosystems that live on the ice edge here, their habitat is getting smaller. And this happens all over the world in different ways, either that habitats are disappearing or that they're moving and changing so fast that the ecosystems don't have time to adapt. I could go on and talk about many more impacts, but what a lot of them have in common is that they're in some way related to temperature change. And for the interest of time, in this presentation, I will focus mostly on temperature change as an impact. So what are the drivers of climate change? Let's take a little bit of a step back and look at the Earth from a distance. So the Earth is receiving solar radiation from the sun in the form of shortwave radiation. And then some of this is reflected directly on clouds or aerosols, but some of it will be absorbed either at the surface or within the atmosphere. And then the Earth emits long-wave radiation going out. And in order to have a climate imbalance, there needs to be roughly a balance between the radiation coming in and the radiation going out from the system. Then if something happens that disrupts this balance, for example, hindering the long wave radiation to escape, then that will drive a climate change. So we call this a forcing, and I will be talking a lot about forcing. And that's a human or natural induced change to the radiative balance at the top of the atmosphere. Okay, so once this imbalance is in place, the climate will start to change. So the temperature might go either up or down. In this case, let's assume up. And that will initiate feedback mechanisms. So a feedback mechanism is something that is caused by the temperature change in and of itself, and either diminishes or increases that temperature change. The most common example of this is the sea ice feedback. So when we have warming temperatures, then the sea ice melts, which exposes the dark ocean surface, which then absorbs more of the incoming solar radiation, which further increases the warming. So that's a positive feedback effect. Okay, so what kind of different drivers of climate change or forcers do we have? So we have some natural ones. Volcanic eruptions have typically a relatively short timescale effect, but it can be very strong depending on the eruption. Changes in solar intensity can be one other natural forcer. And then on the really long timescales, the tilt of the Earth's axis is a very important one. On the other hand, we have anthropogenic or man-made forcings. So on top we have greenhouse gases. Often we talk about CO2. And then secondly, we have aerosols. And I will go a little bit more into detail about these top ones. And then we have other things, like, for example, if we change the land surface, then that can affect the albedo of the surface. So that is how much solar radiation is reflected, and several others. So I'll focus on these top two ones, and it will become clear a bit later why these are good to focus on. So first, CO2. And this is the largest driver of anthropogenic climate change. And there are two reasons for this. One is that we emit a lot of it. And the second reason is that it's really hard to get out of the atmosphere once we put it there. So it's basically like trying to get the toothpaste back into the tube, really hard. And it warms the climate in the following way. So the Earth receives radiation from the sun. Then the surface emits long-wave or infrared radiation. And this long-wave radiation, that can be absorbed by greenhouse gases, for example, CO2. And that will warm the atmosphere. And then this long-wave radiation is re-emitted. But when it's re-emitted in every direction. So some of it is also reflected or re-emitted back towards the surface. And this warms the surface. And of course, this process is super important because it would be super cold and uninhabitable if we did not have that process. But when we're adding CO2, it's basically like putting on too many coats. So it's becoming warmer. So next, let's look at the aerosols effect on the climate. And these can affect the climate in two ways. The first one is directly through scattering or absorbing incoming sunlight. So you see an example of this up here. This is Saharan dust. And as you can see, it's much brighter and more reflective than the ocean surface below. So that will cool the surface. And then the second one is indirectly through affecting the formation of clouds. And not everyone knows this, but each cloud droplet in the atmosphere is formed around a pre-existing aerosols. So when we add more aerosols, basically we can get wider, more reflective clouds. So on the right-hand side here, you see these stripes, and you might think that these are condensation trails, but in fact, these are the effect of ships that have sailed under each of these lines and emitted aerosols to the atmosphere, which have made the clouds brighter. The problem with aerosols is that the overall effect is quite uncertain. And the observations are often hard to use because even though it might look obvious here, there are also dynamic implications, and there's a time evolution, which basically makes it tricky to just take a picture and estimate. And then models often disagree of the magnitude of this effect. Okay, but what are these models that we're talking about? What is a climate model? So I asked my friends what they think it is. And these are the answers that I got. I got, is it a kind of globe? And then I got a computer program which we feed climate data from the past, which then predicts the future. And then I got, it's a weather model just very far into the future. So who's right here? When we make a climate model, what we do is we divide the Earth into a 3D grid. So basically that means that we have a lot of boxes stacked on top of each other, or you can also think of it as a highly pixelated movie. And then within this grid, we try to represent the climate relevant processes. So ocean, atmosphere, land, ice, hydrology, and so on. But then you might ask, why are these models anything like the Earth? So what we try to do is that we take nature and then we chop it up into individual processes. And then each of these processes, we try to describe it to the best of our knowledge with the laws of physics, chemistry, fluid dynamics, and put that in the form of an equation. And then finally, we put it back together again, and that's the climate model. So an example you can see here, this is the Navier-Stokes equation, and it governs the movement of fluid. So we use it both in the atmosphere and in the ocean. Okay, so when we put it back together again, we basically press play, and something like this comes out. So this is not observations of how the fluids move. These is actually these equations playing in and making it look like this. Okay, so which ones of my friends were right? It is a kind of globe. Yes, it's a kind of globe. It's a virtual globe, so that's not really wrong. A weather model, just very far into the future. This is also pretty much true. It uses much of the same equations as a weather model, but because we're looking at different time scales, the emphasis is a little bit different. Then lastly, a computer program, which we feed climate data from the past, which then predicts the future. Not really, even though it's true that it's a computer program, and even though climate data from the past is a super important part of climate research and model evaluation in general, we try to put into these models how the world works, how nature works, independently of what the history of climate change was. So in that way, it's not true that we feed climate data from the past into the models. Okay, so I've been saying climate model, but the title says Earth system model. So what is the difference? Basically, a Earth system model is a more comprehensive climate system. And an Earth system model strives towards representing all climate relevant processes within it. Especially, it has it's supposed to have a carbon cycle, both in the land part and the ocean part. And then often they have more complicated chemistry, aerosols, vegetation modulation, glaciers, etc. And the transition between climate model and Earth system model is a little bit fluid. So it's more like a degree than a sharp change between the two. Okay, so we have all these like very comprehensive, including all these processes models. What's the downside? Why would we not just always use an Earth system model? The downside is that because these models are so comprehensive and are supposed to run for so many hundreds of years to predict the climate in the future, we need to simplify the processes that we include quite a bit. So we do not have the computational resources to represent very fine-scale processes. So that is the downside. So while we as climate modelers often feel that we're super clever putting all this stuff together, then higher resolution modelers often see it as simply butchering and simplifying too much the processes that they care about. Okay, so that was the introduction. Now let's move on to detection and attribution of climate change. Here you see a time series of observationally based estimates of the temperature evolution of since the late 1800s and up to roughly present day. And what seems pretty obvious from this time series is that the temperatures are increasing. But what is not obvious is why this is happening. Could it be some natural reason? Could it be that the sun activity has changed? Could it be natural variability? This we can't see from this picture. So that is where Earth system models comes in. And what detection and attribution studies try to do is that they use Earth system models to explore the drivers of historical climate change. So the nice thing about a climate model is that we have tried to put all these processes into it that we think might matter for climate. And this means that we can run the model with and without the human influence, with and without the anthropogenic influence. And that is what this figure here is showing. So this is from the last IPCC report. And the blue is the climate models run only with natural forcings or drivers. And then the black is the observations. And as you can see, it doesn't seem to fit, like something is not right here. But then when you add the anthropogenic forcings, then you see that the models are really doing quite a good job at representing the temperature change. So overall, what this means is that it's very hard to explain the observed temperature change without adding the anthropogenic influence. But as we've already talked about, there are several different anthropogenic drivers. So which ones actually matter? So this figure here is showing climate models run with individual forcings over the historical period. So on the top, you see the sum of all of them. And then you see greenhouse gases only, see a sharp warming. And then you see aerosols that have contributed to a cooling. And then you see natural, volcanic, and solar, and stratospheric ozone, and CO2. And CO2 is the biggest part of this greenhouse gas up here. Okay, so we want to figure out which ones are important. But there's quite a bit of an uncertainty in these modeled responses, especially in the aerosols here. So when we only look at the anthropogenic versus the natural ones, then we can't really know which ones are important and which ones are not. And let's just have a look at an example here. So we might have one model that has a very strong greenhouse gas warming and a very strong aerosol cooling. And then we might have another one which has a moderate greenhouse gas warming and a moderate aerosol cooling. So the sum would be the same for these two, even though they have very different effects of each of these. So we want to try and disentangle this and see what actually has contributed to the observational change. And yes. So one way of doing this, and there are several, is something called the fingerprint method. And I will explain this one to you here and show some results. So what the fingerprint method does is that we have an observed change, for example, a temperature change over time. And this is a synthetic data set that I made, so it's not real, as you might see. And then if we say that we have two forcers, for example, that we want to check which ones have influenced, then we can run our Earth system models with each of these forcings individually. And then what we get out is a fingerprint for each of them, or a pattern. And then what we assume with this method is that the observed change here can be written as a linear combination of this first fingerprint here, plus the second fingerprint here, and plus some internal variability or climate noise. So that's the equation down here. And now we can solve this equation. And in this case, it would be 0.8 times x1 plus x2. So what that means is that according to this method, the forcer number 1 is slightly overestimated in the model. So it has to be scaled down a little bit to fit with the observations. But forcer number 2 is pretty much spot on. So this is illustrating the advantage of this method. So we're assuming that the models managed to get the pattern more or less right, but we're not assuming that the models manage to get the magnitude of each of the forcers right. And that's an advantage when we have very uncertain processes. Okay, so let's have a look at a paper. These results are from Gillette et al. 2021, so it's super fresh off the press, and they're using CMIP6 data, which are the latest generation of climate models. So they start out with a two-way regression. So they're using just anthropogenic influence and natural influence. And then they're doing this for each of the CMIP6 models. And these are the regression coefficients on the y-axis, so basically A1 and A2. And what I just want to say first is that if A is indistinguishable from 1, then we say that the model is consistent with the observations. So that is that the forcer is roughly the right magnitude. However, if A is indistinguishable from 0, then we say that we cannot really detect the forcer because we cannot reject the null hypothesis. That would be that the forcer is not important. Okay, so let's look at the results. So the anthropogenic is detected in 12 out of 13 models. The only one where it is not is this axis ESM here, which has a very unrealistic historic evolution of temperature. And then the second thing that we can notice is that these models in blue here, they are underestimating the response to anthropogenic. So that means that to fit with the observations, the anthropogenic forcing needs to be scaled up. And then similarly, CAN-ESM is overestimating the magnitude of the anthropogenic influence. Okay, next thing they do is that they split the anthropogenic signal into greenhouse gases and aerosols. So now we have a three-way regression. As you can see, it's suddenly a lot more noisy. The aerosols and the natural influence is not always detected, so it's not always significantly different from 0. But on the other hand, we can see something interesting, which is that in quite a few of these models, there seems to be these kind of compensating errors that I was talking about earlier, where both the greenhouse gas influence and the aerosol influence seems to be overestimated by the models. And then on the other hand, you have this model here, where both are underestimated, and this one is almost significant, and this one is almost significant. Okay. So in general, the multi-model mean does better in climate science than any individual model. And part of it is because we reduce noise, but part of it is also that somehow the multi-model mean often does better. So let's have a look at how the multi-model mean does. In terms of the regression coefficient, we see that the anthropogenic warming is consistent with the observation, but that the natural influence is not detectable. On the other hand, in the three-way regression, we see that both the aerosols and the greenhouse gas are consistent with the observations, but that the best estimate for the aerosols are that the models are overestimating the effect of aerosols by roughly 30%. So that's quite interesting. And then next, if we look at the attributed temperature change, then we can see that according to this method, all the observed temperature change is attributable to anthropogenics. But secondly, when we do the three-way regression, we see that the greenhouse gases would actually have given a lot higher warming were it not for the compensating effect of the aerosols that have been cooling the climate at the same time. Okay, so let's sum up part one. So we've seen a method of how to use Earth system models to attribute the observed change to different drivers. And then secondly, we've seen that the anthropogenic drivers are dominating the recent temperature change. And then lastly, we've seen that the greenhouse gas warming has been masked by aerosol cooling over the historical period. So moving on to part two, using Earth system models to predict the future. As we move into the future, there are a lot of sources of uncertainty. One of the maybe most important ones are actually, what are humans going to do? So are we going to emit more greenhouse gases, or are we going to mitigate our emissions? And how we tackle this in climate science is that we try to make these scenarios for how humans will behave, or shared socioeconomic pathways, as they're called now. And here you see the CMIP6 models, latest generation of models, and how the temperature changes towards the end of the century. And on the right, you see the precipitation change in the different scenarios. So then you can see that if we follow the business as usual scenario, it gets really warm. And then if we follow a very strict mitigation scenario, then there is not that much warming. But secondly, there's the shading around each of these scenarios. And that shading shows the spread of the climate models, or the Earth system models. And it's quite large. You see that it's actually overlapping the scenarios. And towards the end of the century, one of the things that really dominate this is how the models respond to changes in greenhouse gas concentrations, and in particular CO2. In climate science, we have an estimate for this, or a parameter for this, and it's called the climate sensitivity. And it's defined as the temperature impact on the Earth when we double the concentrations of CO2 since the pre-industrial levels. Okay, so here you're seeing a graph of the increase in CO2 concentrations since the 1960s from Mauna Loa. And then you might think that a doubling of CO2 is a very high number, but actually it turns out that we're already halfway there. And this year we reached 420 parts per billion, and that is halfway to 2 times CO2. Okay, so let's have a look at this climate sensitivity and how it looks in the models. So these results are from Selinka et al. 2020, and they're comparing CMIP5 and CMIP6 models. And here you see the models in each of them and their climate sensitivity. And what we can notice is that CMIP6 has a lot more very high climate sensitivity models than CMIP5. And notice the scale here. This is almost 6 degrees warming. That's catastrophically warm. So we really want to know if we can narrow this down somehow, if there is anything we can do. And then lastly, I just want you to notice that the radiative forcing, so the forcing from CO2, hasn't really changed that much. So this is mostly about how the climate system responds. Okay, so can we narrow it down? One method that I want to present to you of doing that is so-called emergent constraints. So basically, it's asking if we can make a better estimate of the future by looking at what the models do in the present. So we take some variable x that we can observe in the historical period, and we try to establish a relationship with a variable y in a future simulation. For example, the climate sensitivity. And then each of these dots here would represent a climate model. So if we establish this relationship, then we can say that we have some observed x plus minus some uncertainties. And then we can use these observations to say that these models up here, not really that realistic. So it's much more likely that the real variable y in the future is within this range. So let's look at some results, also from CMIP6 models, showing this. So Tokaska et al. 2020, they use this period here, and then they use the temperature trends in that period to as the observable x. And then they try to make a relationship with the climate sensitivity, here the transient climate sensitivity, in the future. So that is what you can see here. And then I just want to say that they choose this period here because that's a period where the aerosol forcing is pretty stable. It's not changing that much. And then they say that it's reasonable to expect that this temperature change that we observe is mostly from greenhouse gases, and then it should be related to the transient climate sensitivity. Okay, so let's look at the results. Here you see the individual models, both from CMIP5 and CMIP6, and then you see their color is their climate sensitivity. And then the gray area is the observed temperature trend. So basically what they find is that these models that are up here, they are not doing so well in representing the observed temperature trend. So they constrain the likely value of the climate sensitivity to a much smaller range. And there have been several of these studies, and a lot of them conclude similarly that the high equilibrium climate sensitivity models seem to not do super well at representing the historical evolution. However, we have to be aware that there are not that many data points here, and there might be systematic ways in which we structure our models that lead to this. And in essence, we just need to understand better why these models up here have so high climate sensitivity before we can disregard them as unrealistic. Okay, so climate sensitivity accounts for the impact of CO2, but it doesn't account for the aerosols. And like we've been saying, the aerosols have been masking the warming from greenhouse gases, but as we move into the future, air quality reform, concerns for human health are going to decrease the emissions of aerosols. So we've always seen this in Europe, and now we're seeing it also happening very fast in China. This figure here is showing the change in aerosol optical depth, so basically how much aerosols, between 2015 and 2018 and 2010 and 2013. So it's a really small change in time, and the changes are very big over China in particular. Okay, so does this mean that all this cooling, is that going to suddenly flip into giving us warming in the future? It does seem so. And I'm going to show you one example with a climate model showing this effect in the past, just to illustrate how it might also work in the future. So what this study did is that they ran the Norwegian Earth System model with and without the historical reductions in European emissions of aerosol precursors. So then this is the reduction and this is the fixed European emissions. And then this is what they got out in terms of temperature change. And it's really quite interesting to see how this change in European emissions have actually, according to this model, quite significantly contributed to Arctic amplification. And this also illustrates another thing with aerosols, and that is that their effects are quite local. So as we're going into the future, decreases in aerosols in different regions are going to affect the climate in different regions differently. And then lastly, I would like to note that Samset et al. From 2018, they also use models and show that if you remove all the anthropogenic aerosols, this might go as far as resulting in a 0.1 to 1.1 degree warming. Okay, so let's sum up part 2. Firstly, future warmings depend on emissions. Secondly, climate sensitivity increases in CMIP 6 versus CMIP 5. And next, emergent constraints in general prove that high climate sensitivity models seem to not be so realistic. And reductions in aerosols in the future are likely to lead to warming. Okay, so finally, let's have an outlook and look at the futures of Earth system models. So I would like you to consider 2 different scenarios here. One is that Earth system models should continue along the road that we're a little bit already on. So they should seek to become more comprehensive and include more uncertain processes, for example, within the realm of the biosphere, ecology, or even the economy and human decision. And the second one is that the Earth system models the Earth system model project should basically be abandoned, and we should rather focus on making super high resolution and computationally heavy models that reduce the number of uncertain processes. So I'm going to start with the second case, the case for simpler, higher resolution models. And this is made by Palmer and Stevens in a piece from 2019. And they argue as follows. So here you see the temperature anomaly in the observations in black, and then you see the CMIP 5 models in all the colors here. And it seems quite good. They're more or less managing to capture the trend of the temperature increase overall. But then notice this part of the plot that at least I haven't noticed before. And it's showing the mean temperature in the models between 1961 and 1990. So not the anomaly, but the mean. And there you can see that even though they're pretty good at the trend, actually they're pretty bad at the mean. And the spread in the mean is larger than the actual temperature increase over the historical period. So these models are basically not so good at actually modeling the climate that we experience. So let's have a look at another example. These are the multi-mean bias, so how wrong the models were in CMIP3. So that's an early generation of climate models. And then this is the same, but for CMIP5. And then this is CMIP6. And this is for precipitation. So the question is, who can really tell the difference here? We've added all this increase in complexity and increased number of processes. And then a basic property like the precipitation is quite similar through all of them. So what Palmer and Stevens suggest is that a fresh wind in the form of a step change in the physical content and fidelity of climate simulations systems must be let loose to fan the flame of the basic climate science, to challenge our understanding of how global warming becomes manifest in regional climate and its subsystems. So they propose that we should rather have high resolution models, approximately 1 kilometer, that is 100, so what we normally have at this point. And then the advantage of this is that we can resolve more processes directly, for example, convection and storms. And then we can also reduce the number of subgrid processes, and they want to simplify the ones that are left and represent them stochastically. Okay, so on the other hand, resolution is not necessarily everything, and fluid dynamics is not necessarily everything. So I want to make the case for the more comprehensive models from the side of the carbon sink of the land and the land in general. So this plot here is showing the partitioning of the CO2 emissions. So you have emissions, and then you have where does the CO2 go. So we see that quite a bit of it is going to the ocean, some of it is staying in the atmosphere, and then you have this land sink here. And as you can see, it's very variable from year to year. And furthermore, we expect it to change in the future. So permafrost, for example, forest uptake when the temperatures are warming, what happens with insects, and so on. So Bonin and Doney argue for a more comprehensive climate model, and they say that Earth system models are an imperfect but necessary tool to study the net effect of forests. And if you want to, for example, plant the forest to diminish climate change or mitigate climate change, then you have so many processes to take into account. You have the surface albedo, how reflective the surface is, the carbon uptake, the evapotranspiration, which translates into atmospheric moisture and also clouds. And you also have aerosol precursors in there. So basically feedbacks that require a land-atmosphere coupling. And they argue to actually include even more processes like insects and ecosystems. And then they say the following, which I think is nice. As terrestrial and marine ecosystems have been added to Earth system models, the distinction between the physical basis for climate science, mitigation and vulnerability, impacts and adaptation no longer necessarily hold. So I will leave you with these two future roads and not really conclude on it, and go to my summary. So firstly, Earth system models are needed to study the big picture of anthropogenic climate change. They are used both to understand the past and to explore possible futures. Uncertainty is very high, especially concerning how the Earth system model responds to greenhouse gas drivers, in other words, the climate sensitivity. And then lastly, aerosols have masked the warming from CO2 greenhouse gases, and this effect will likely turn into a warming in the future. And finally, the future of Earth system models are also uncertain. So that was all I had. And thank you very much for following my trial lecture. I will now go through the references for the video. So these are the references that I've cited directly. And then these are background literature that I used and further reading.